I should hide those. Jesus, you guys are.
Really, in like, not that they're like easy. I mean, recognize that not sure. Like, they're like
Okay, so we are back. We're back to system calls, and I'm trying to record, most of it will be the board, but there'll be a couple of slides. So the people who missed last week, so we were mostly talking about what I forgot already. So we didn't talk about system calls, but we were talking about how we essentially load an elf, so which will be the next homework. So I hope it got recorded reasonably well, so you can review. I tried reasonably hard to record it. So are there any questions about the homework, which I said is due today, but I'm happy to move it forward just because because no one volunteered on time to do the auto grader, but we have a volunteer. But okay, so yeah, let's move it so to what date? Like Wednesday or even further? Wednesday sounds reasonable then. At least as the first step that we can iterate, if anything. But let me help. Let me know if you need to, like, if you have any specific questions.
Processes, so like nobody can actually. So I guess the main way to sort of whether
it's not as hard. So like our plan for testing, like for grading, will be to ask you to have a function, something test to borrow, and we will replace this function with our own code. But essentially inside you have to test for whether box works for different sizes, whether page allocation works, like just whatever. Like you can use it as that global alloc interface trait, right? So just use those alloc and free methods to allocate objects of different sizes, or use the methods of like internal to your allocator and allocate essentially custom for K pages 2 MB pages. Ideally, try to trigger the split and merge events as well, but it doesn't mean that it works. It just means that we tried a little, right? Because to test, like testing is a whole different discipline, right? I forget, like it was you or someone else. I discussed it in person, and it's very hard to test an allocator. You really have to, like it's like FODS testing, but beyond, right? So FODS testing will only give you so much. So it has to be on steroids. Allocator is hard. I mean, this allocator is easy, but essentially just do those tests. And again, like we're not gonna test anything like crazy. Just the point of this homework is to get something working. It's not like a production quality allocator. Makes sense? Anything else? So some people were asking online, they cannot create, like when we do this page array in memory, which we like dynamically kind of make up out of nowhere. Like at this point, when you know the size, you can just use this pointer and do an unsafe typecast. Like similar to how you would do in C and say, look, I typecasting to a data structure of a specific size. You can also do typecasts to individual elements if you need, right? So this is where kind of like Rust kind of breaks apart a little. So the safety of Rust is against you, and you're saying, okay, I'm willing to risk and make a mistake, right? There is no other way, honestly, because you want to do like a double linked list, which the Rust type system safe subset of Rust does not allow you to express. So you'll have to use those pointers in an unsafe manner. Like we can. It's nice to talk about whether it makes sense or not, right? So you can say, look, But the whole promise of Rust was that it will be safe. And now you tell us write unsafe code. But in reality, like most of the Rust which you see is built around like small unsafe core, which exposes safe abstractions, right? Like RC, arc, like anything what you see, like mutors, vector. Vector is internally unsafe and internally, right? That's a reasonable split. So ideally, you should try to create a similar set of abstractions which somehow route those unsafe operations in a safe interface. But again, you can only do so much, right? So that's okay what I meant to say here. In my view, the future of Rust is not really like I would like I was a big fan of safety. In this project, Bradley, we tried to build a microkernel which minimizes the use of unsafe. And that came from a different microkernel, which is called TOC. It's from Stanford, which used them in less unsafe, to the point that their list abstraction was a single linked list. And in order to access a specific, delete this element or something, they had to essentially walk the list to make sure that they know the grab or something like that, right? Because there was no pointer to the grab element or something. So which introduced this O1 complexity or N complexity, right? And then it turned out that despite the fact that we tried to minimize the use of unsafe Rust, the amount of unsafe, even the stuff which I had here on the board, like vector, mutex, arc, it's large enough that if you start looking very, very carefully, it will be hard for you to convince yourself that this code is absolutely correct. And the only way to solve, and there are bugs in standard life, right? Essentially, the argument which one can make today is that with modern verification tools, you can actually reason about this allocator and convince yourself that the code is not only safe, but also is functionally correct, meaning that it does what it's supposed to do. And that's a stronger argument than just being safe, right? Because you also know that, I'll give you a simple example. For example, like lists are safe in Rust, right? But like the Rust, you cannot do this, but like maybe it's not a very good example, but you can have functional properties like list doesn't have cycles or something like that, or each element is. So that's where we're going to hopefully in the next in the near future, and people are working on verifying standard library. We have a verified implementation of this allocator, which I'm asking you to build. So hopefully we'll get to that implementation. I'll be able to show it in class, right? So, but yeah, so on, like, there is a lot of unsafe code in the kernel. That makes sense. So just at this point, like, okay, Rust, C, just do whatever. But like, I don't know, like, try to spell out the argument why certain operations are safe, you believe. People usually just make an informal safety argument in the text or something. Okay, any other questions? Yeah, so typecast is your friend. This is how you allocate this list, essentially. You allocate elements of the list similar to how you did in x86. Essentially, you say, look, I will start walking this memory region, adding one element by one to the linked list, so right, starting from this one and so on, right? So that's how you will initialize the linked list. Okay, but back to Syscall. So what we were doing last week is that we were talking about how we can create the first process, and essentially our tricks were we're gonna compile initRD kind of style memory file system, which is not just memory file system. We just will initially just simply put an elf of the first process there. We'll load it from the kernel. We'll implement this one system call, which is like create process 0. Elf gets here. We'll have your own text data sections. We talked about whether we need to set up the stack or not, and we said, okay, maybe we don't even have to set up the stack because we're so clever that we we're not going to pass arguments on the stack. And so the program, when it starts, doesn't really need to have a stack. And instead, it can do like a very first syscall and essentially mmap some memory for the stack itself, and choose its own stack size, figure out how many stacks, choose its own address space layout. The microkernel doesn't fix the layout of where the stack should be, right? So, and sure, that's kind of elegant. So, but this immediately brings the question, can we even how to support system calls? And I'm kind of arguing that maybe the very first system call which we have to support is even printf, just to see that the process is running, right? And so today we're talking about the mechanism which allows us to implement fast system calls in this modern 64-bit systems. Make sense? Okay, cool. So just to warm up a little, so how did we implement system calls in x86? Keep asking this question, so by now everyone should know. Which hardware mechanism are we using in x86? Interrupt. So in x86, we said, okay, int instruction with some number, in x86 is 64 or x40, will trigger a system call transition, meaning that when you do an int, the hardware will go through the IDT, and this entry x40 will be configured in such a manner that this privilege level flag will be set to 3, meaning that user can actually invoke this interrupt, that's okay, and then it takes you to the syscall handler. And of course, since you have a CS entry or code segment entry, this one takes you to the GDT. And in GDT, you take a CS entry which has privilege level 0, meaning that it's now you switch from PL3 to PL0, right? Makes sense? And along this path, you also use the TSS entry in the GDT to figure out the pointer to the TSS. And from the TSS, you will have a pointer to the thermostat, right? And we talked about it last time, and we said, okay, this is fine, but it's not ideal because historically this mechanism was probably, there is nothing really wrong with it, but just it's kind of slowish. And even I think one-way transition is roughly something like 350 cycles on modern machines, right? And if your program has a ton of system calls, you ask yourself a question okay, sure, can it be done faster? And so Intel came up with a slightly faster mechanism. So what does anyone know the name of this new instruction, which Intel implemented for implementing essentially bypassing all of this business, but building the system calls a little faster, a little differently and faster. Don't remember the name, so I mentioned it. It's called a syscall instruction. So roughly speaking, it is, I think, and I mean, I did measure those numbers, but decades ago. So I don't know if the numbers are up to date. Maybe they grew a little, but maybe not. But the syscall numbers, they're roughly 100 to 120 cycles. Actually round trip. So I don't think, I forget how I measured for int, maybe it's 1 with. So, and that's pretty cool, right? So 100 cycles for a system call is reasonably fast. It's not like a function call, which is like 5 cycles or something, but this is reasonably fast. And so that's why I say, look, all modern operating systems will use this mechanism for implementing system calls. And it's worth digging into it because sitting with int mechanism is nice, but probably not realistic as of now, right? And so what is this syscall does? So syscall is a way simpler instruction. So what it does is that instead of using this diagram and following this layout, what it does is that okay, sure, Intel has a limited number of registers. They are called model-specific registers or MSRs. So they have this human readable names, but really they're just numbers. And you can use write MSR, read MSR instructions like write MSR and read MSR to access those registers, and which allows them to extend the CPU. It's not just one IDT register. It's endless amount of model-specific registers, right? And so they say, okay, look, there will be one register, IA32S star, which will contain, among other things, these code segments. So now this register will be pointing to the GDT, right? To here. Make sense? Drawing over. So this is what. If you ask me, do I know the names of those? Do I remember those by heart? No. But that's okay. It's easy to look up. Sure. Because like this is instead of int something to do with syscall at user level. So instruction is unprivileged, right? And the end goal is that you will transition to the handler, right? By passing those mechanisms. Instruction pointer is picked up from a different register. So this one is IA32L star. And I don't even remember step. So this points to the handler. And there's another register which is called IA32 mask flags. And this one, don't even spell. It says which fields in the R flags register should be masked, meaning that it allows you to, if you set this bit, it will disable interrupts automatically on entry into the handler. Right. And the expectation is that the instruction does it all. So it saves the previous instruction pointer in RCX register, saves the previous value of R flags because you're setting it forcibly with this possibly into R11. Privilege level changes from 3 to 0, no intermediate privilege level changes, so you cannot jump into 1 or 2. And stack pointer is not changed on entry automatically. So you have to be careful and make sure that you change the stack pointer in the handler when you start running. Question.
Where do all these registers that we just overwritten get saved? Like, can you get at the old RCX?
No. There's no old RCX. So you should push it here. It's your convention, but it's kind of clever. You say, look, why do they have to save? Why do I have to make everything transparent? So like, yeah, if you feel like you need this, then please save RCX. And if you do exactly RCX is a caller or caller saved, there should be like probably the logic is that it's caller saved. That's why you have to. It's not guaranteed to be like logically. I'm not 100% sure. I remember, but logically, you would pick a register which is not guaranteed to be saved right across the boundary. So that's why you say if you wanted to save it, if not, well, don't save it. You save one instruction or like 2 cycles literally by pushing it on the stack.
Does the CPU save the old value somewhere that the supervisor can't access and then says thread restores them? Or does it still apply?
I think you cannot get if it's unsafe, then it's gone by step. There's no. If you're saying, okay, what if the question is like, why would you need in a normal situation, if it's not a page fault or anything like that, why would you need to access this value, right? So there's nothing really specific about it. It's okay to have a register which doesn't have any useful information. Pick any other registers to pass arguments or stuff like that. But it like this minimalism allows you to really save some number of cycles, and like this kind of like makes sense. I would say until that seems like the right design choice to me. I don't see a huge mistake. The other questions, do we understand how it works? So it's a little faster, right? A little faster than going through the IDT, picking something from the GDT, stuff like that. So although you do pick the code segment from the GDT, and in fact you also could pick the stack segment. But the stack segment is, interestingly enough, and I don't know if it's a good choice or not, instead of like saving it somewhere, they just say, look, guys, we will just make an assumption that the stack segment is the value of CS, which is the same bits, plus 8, which means that it has to be the next entry in the GDT, right? So remember, when we were talking about GDT, I was saying, okay, the order of those entries doesn't matter, because it did not matter up until now. But suddenly, if you want to use syscall, then this data segment or a stack segment should follow the code segment. And this plus 8 is because the lower 3 bits of this kind of value, CS value, are some flags, and that's why plus 1 is plus 8. Right, step correct, right? Makes sense? And plus, it's nice. It's also nice that it's kind of like also logically follows that this is like 8 bytes wide. Okay, so we got the code segment instruction. So this is the three MSRs which are involved in this transition. Those are the numbers. Say you need to remember anything, just essentially semantically remember that one says code set, one provides code segment, one provides the pointer to the handler, entry point in the kernel, and one says, okay, I can really disable interrupts by masking the interrupt, by setting the interrupt flag, right? Or by disabling. Okay. So there is one interesting detail here. No, not that it's a detail. I just want to come back that the only two things which we cannot recover are the values of the instruction pointer, because if you don't save it, like there are probably mechanisms to figure out how to return by saying, okay, I know that like you can make a contract with the user level saying, I always return to a specific address. That's kind of cool. And second is R flag, because the moment you change it with this register, you don't know whether it's but other than that, everything more or less fine. Makes sense, right? And then your syscall entry point, obviously, you say you need to figure out the stack somewhere, right? So it's a sequence of this assembly instructions. And at the high level, you get to this syscall dispatch function in the kernel. So you will have some kind of a assembly trampoline which carefully saves the state, but then go to a generic syscall dispatch function, which says, okay, depending on the syscall number, for example, you can make an agreement that the user level passes the number of the system call in the RX register. And then you say, wow, you execute a specific kernel function on like based on this value, right? So that's the end goal. But the intermediate goal of this trampoline is to save the state, right? And in order to save the state, obviously you need to figure out the kernel stack, right? And roughly speaking, so how will you figure out the kernel stack? You say, look, I will be using the global variable, something like kernel stack point, right? And I will load it in the stack register, right? After that, you have a stack, and I will explain what the other instructions in the stack. And then you can say start saving. Here you can use the before. What do you do here? You first have to save the user stack because you want to store it, so you can save it in a global variable. Then load the from a global variable into the RSP register the new value of the kernel stack. Okay, maybe we'll take a look at the real implementation, but then you start pushing those user R flags in R11, RCX, user RSP, but you can choose the layout, and you can choose the layout which you want. And then save general registers if you want them on the game, which is the layout. And then call the C-level function, passing it. Like again, you should figure out the calling convention, how you want to pass the arguments. But we'll take a look at the real implementation to make sure that it works. Right? Yeah. My question was, what is this instruction? I don't understand it fully, but that's okay. But we will take a look at a real example from which we wrote, which takes slightly more. Which makes more sense. The reason I bring up this example because I wanted to highlight this syntax. Yes, colon something. So what is this syntax about? Can you guys guess? Oh, yeah, no, sure. Anyone else? Any other LLVM people? Say again? Global stack. No, global stack looks like global stack is this kernel RSP variable, right? But why is it like, why do we write a GS colon kernel?
So it's a relic from the days of segmentation.
Mhm.
GS is one of the segmentation registers. There's also address. And it says which address space to use. And stored in GS or FS is a pointer to an entry in your GDT.
Mhm.
And it says how to resolve the address on the right-hand side of the kernel. So kernel RSP is some address. And the GDT entry
So
says
GS is non-zero, so it will have some value, right? And this value is added to kernel RSP, right? But do you know why we're doing this? Can you guess? You guys should.
well, the GS points to the kernel stack in the GDT. It's your offset.
No, GS points to, well, not exactly. That's a good thing. So this GS, which I'm just using in this column notation, really points to this entry in the GDT, right? But this entry in the GDT is just a regular entry, which is from 0 to, no, it's actually, this GS doesn't point. This GS points, I take it back. It doesn't point here. Sorry, I get confused. No, but wait, this syntax, like you never seen this before in modern programs, VM stuff, when you specifically try to like break something, some DRM protection or something. Sometimes these registers are like UA used to do. Correct. So this is for TLS. Why in the Hockey way? That's how it's implemented. So at user level, this syntax usually hints you that this is a thread local variable. And GS will be pointing to the section which is responsible for holding thread local variables, right? And why are we doing this in the kernel? What do you think? Just try to guess real quick. Okay, so we're gonna use GS to hold similar to thread local variables. We'll be using it to hold first CPU local variables. Right, so this is a common idiom in a kernel that on each CPU, you will have a collection of variables which are private to this CPU. So like maybe a pointer to the current executing thread, right? And you say, look, on each CPU, this pointer will point to a different data structure in the kernel, like T55. On this CPU, it will be pointing to like T17, right? And because all of these CPUs are executing at the same time, you say, I want to have those, it's similar to thread local variables. It's kind of like per thread. But really, like, again, you can build your kernel where you have both per thread and per CPU variables probably. But in the kernel like Linux, typically you just have per CPU variables. It's typically it's enough. So there is nothing like thread local in a kernel, but like there is local to a CPU, right? And we saw it earlier in this class where I demonstrated how Jafang created a like CPU data structure, and it was showing up in homework too. So essentially, Jafang did CPU, and he did some fields here, and he said that each CPU, this is the only thread local variable, and then he said, okay, there will be an array of those in the system, and on each CPU, when I'm booting, I will set GS to point to a specific entry in this array, right? I don't know if you remember this code. I can come back to it in a second, right? I can look it up. Makes sense? And then if you say GS something like some field A here, then it means that if GS points to this instance of CPU data structure, then you're using this specific A field, right? And the compiler will generate this code, right? Makes sense? And there are multiple ways to build these abstractions, right? So as I was saying, Jafang simply says, okay, in this atmosphere kernel, which I keep referring to, he just said, okay, there will be one. Let me just maybe open it just to make sure that we have a concrete example. So this is the openly available version of Atmosphere, which is not the best, but we released it as part of the artifact evaluation. So if I do something, if I go somewhere like into the kernel source CPU, this is what Jafang is doing here. So he says, this is my data structure, which he calls CPU. And all these fields will have a different value, like because we will have a different instance of the CPU data structure on each CPU, right? How we access those fields, we say, by the way, he says also my stacks will be part of it, right? So this data structure is quite large because he says, okay, I will have 7 IST stacks as part of this data structure, a syscall stack as part of this data structure, but he also has something like a local pointer to the global descriptor table. Not sure why. Oh, because he probably wants to have a individual GDTs point to different TSS data structures, right? But something like he also said like state of like this was called probably context in x86, essentially just registers of the currently running thread. Where does he have a specifically running thread? I'm not sure, but we can figure it out. But and then in order to access those, he relies on a collection of macros. He says, I will implement this get current CPU field. And this get current CPU field is a macro, get current CPU offset. This get current CPU offset generates the code, which uses this GS. And I forgot how he computes the offset specifically, but no, it just like uses this offset, right? So it's instead of like relying on some compiler support, which give me the access relative to GS, right? Makes sense? So, and then like he can, for example, use a similar trick to say, look, GS has a specific instance of the kernel stack on this CPU, and I will be using this as an assembly to access. Makes sense, right? That's one way to build it, like slightly kind of deviating from the main course of my lecture, but I'll provide this link to this macros, but you can say, look, this is fine, right? And he says, okay, I support maximum 16 CPUs, which is not great, obviously, and stuff like that. So what's the advantage of this? Okay, I'll ask it differently. Do you guys remember how thread local variables are declared in Rust in general for user level? How is it declared for C++?
In Rust, you use a thread local.
Correct, thread local. And you can, like, literally, let me switch to a slightly different kernel, which is Redleaf. And if we do something like why? You can write the code, which is literally just this macro, thread local, and then some variable, right? So do you know what happens under these when you use this thread local? So again, not an expert, and this is when I said, okay, I will need your help, but really, LLVMs like knows of this trick, and it says, look, I will be using this technique, which is called TLS lowering, which essentially says, okay, I expect that you will generate text for TData and TDSS sections and thread local, essentially data and thread local DSS sections, and essentially it will be using this style of addressing for a variable in this section. It will be using JS colon something, right? So, and again, so you can, I'm not an expert. I know that it works in Rust. So if you do this thread local foobar, then it will result into a JS foobar, and this JS foobar will point to some location in memory where foobar will be allocated, right? Makes sense? Okay, so you can use the same thread local macro in the kernel, and the compiler will happily generate a similar code, for example, right? What's the advantage of using this technique versus just declaring a single data structure like Zafang does?
It makes it so that you can place them anywhere in your code, and it coalesces them into the equivalent of this.
Correct. So essentially what Tale is saying is that really Zafang has to be very, very careful about picking the fields, putting this in those data structure. And if you're writing some device driver, which you're writing 5 years later, you have to communicate with everyone that you're changing this field because you need your own foobar in this data structure, right? Which is okay, and it works for small kernels. Like it will work for a microkernel. It will work for a microkernel which Zafang wrote or we all wrote. But if you have a giant kernel which is Linux, then you better have something like this where you say, look, I can really declare a per CPU variable anywhere in the kernel code, and then the compiler will lift it and pick it up from there and just put it in some specific section which is called data. Make sense? Question.
Is there some reason we use JS instead of that? Like, is there a difference? I'm mostly referring to the.
Yeah, let me just get back to it. I have partial understanding, but I will try to explain. Just a sec, right? Okay, we got the advantage, right, of this approach. The disadvantage is a little harder to guess. And I mean, I should have probably communicated with Zafang, but Zafang graduated, so it's hard to get hold of him. Once a week, he replies, Zafang. Yeah, so when you start using this thread local macro, you create a dependency on your compiler toolchain. Meaning if you want your kernel to live happily for many years on multiple architectures like ARM, RISC, whatnot, you are asking the compiler to implement this thread local. And it's an interesting assumption. So I don't know, like LLVM community, like essentially, if we discussed before whether this syscall convention is useful in Rust, so I kind of argue that this trick is more useful. And if the LLVM community signs up saying, okay, we're gonna support it in a specific manner forever, then let's go with this trick. If we don't trust the compiler, then we'll probably have to make something like our own. And there is a trick probably to meet these two in between, where you can declare a macro, where you can create a macro instead of thread local, use your own macro, which puts this in a specific section. And I should explore, but this is essentially the way Linux does it in the kernel. They use a per CPU macro. I forgot exactly the syntax, but essentially the macro itself takes a variable and then expands into like saying that this variable should be added to a specific section, which is T data, for example, right? And this is how it works in Linux. And we can play a similar trick in Rust, but like my goal here is to teach you kind of the spectrum of those solutions. So if you see either as a func trick or thread local trick, which people disagree on whether it's the best way to go because it creates a dependency, especially in a small kernel, maybe it's not even needed, but let's just look at it. Or your own self-baked macro, which adds a variable to a specific section, but I don't show how to do it, right? So just wanted to make sure that you understand all of it, making like if you ever see the code, you know how it works, right? Okay, so any questions on this for now? Now let's one slide back. So what we're doing here, we're like doing this detour on per CPU data structures, some history about what was happening with segments. Essentially, when AMD and later Intel transitioned to 64-bit machines, they said that since in normal case, all these entries in the GDT have bases and limits set to 0 and max, essentially no one uses segmentation. We're not going to even support those in hardware because it's, I don't know, complicates our hardware testing or something like that. So we assume that all the segments which you use in your code always have base of 0 and a limit of max. Besides these two, FF and GS, and those two are special. So they do have bases, but you don't configure those bases through the GDT. In fact, as we were creating a GDT, we never really like even put anything in the GDT with a non-zero base, right? So instead, Intel says, okay, you're going to be using specific instructions, write FS base and write GS base, which like write those MSRs, so right? Like a similar MSRs, two special registers, and those essentially contain the bases for FF and GS, right? And the reason they did it because I think those FF and GS were already used for thread local storage in the user level, so they were always containing non-user bases, or in most cases, and so they left them be like that. I don't know the history why specifically they chose two. And so specifically, Linux uses FF or TLS for user space thread local store and uses GS for per CPU kernel data structures. And maybe that hints for why they left two. So they can use one for user level and one for the kernel, right? Although it's not like an elegant design. You would, I don't know, like create a register with this TLS3 and TLS4, TLS0 to like hold this basis, right? Right? Okay, so we have two registers with non-zero bases, and they are written and updated through those MSR registers, right? So what happens then? Like, how do you even create what kind of runtime support you need to make sure everything works? Let me ask this question for a second. So imagine you have a bunch of those variables which are using this thread local macro. Similar to this one, for example. So compiler assembles them in a specific section. What do you do next in your operating system to make sure that this works? that you can access those variables. What do we need to do at the level of the RAM?
Do we need to copy an instance of that section per CPU and load the address of each into GS whenever we swap to that CPU?
Correct. So essentially, you got the point. So what Jafang will do every time he boots on a CPU, he will call a function which is something like I forget exactly, but something like CPU init or something. Like something like this, where it essentially where he writes the GS base with the address of this specific instance, the CPU instance of this. Since it's not just a single data structure, we have a whole section. Then when we early on boot from the main, before we use any of those variables, we have to be careful. This section will be sitting in memory. You essentially say, look, I will make copies of this section on each CPU, right? And like by then, which is the elegant part here, is that you know how many CPUs you have in a system, so you don't have to fix yourself to some fixed number. It's similar to how we query the bias. So here we'll query the advanced programmable interrupt controller. It will tell us the number of the CPUs. So essentially, you copy the instance of this T data plus the SS sections, and logically, like it makes sense to like if this is your kernel, this is your end symbol, and we already used a little bit of this memory to relocate the ELF binary, right? Because the ELF of the domain 0, because we don't know where grub put it in memory, so we just copied it here. Then we move the end logical end here. Then here probably it makes sense to create this instances of this T data and such for each CPU. And now you will have your end symbol here. And on top of this, you will allocate your page array, right? Make sense? And so every time you initialize a new CPU, on that CPU, you will like write this pointer to the GS base. Make sense? Rick?
Do you recommend that we do this setup before our allocator is initialized or using it?
Like I would say, do not allocate this memory from the allocator. I would say just allocate it, use some kind of magic by passing the allocator. So I say before, it seems easier than like patching the allocator to say that this memory. I think both approaches are doable. I don't have a strong opinion, honestly. If you say, look, like first of all, it may not fit into a 2 megabyte page because who knows how big it is, right? So then, you cannot even allocate consecutive memory. So other than that, it probably doesn't matter. You can go either way. But if I were you, I would just like early in boot, just think of, because maybe your allocator uses thread local variables as well, right? So you have to initialize this GS base before any of your code touches any of the thread local variables. And they are not marked in the code in any special way. That's like the beauty of it, that everything is uniform. Just start using them without even worrying, right? So make sure that you're extra careful. And this is also a disadvantage of this approach, is kind of like a double-edged sword. So like here, you always know that it's all accumulated inside the CPU, and here like any name can be thread local, right? It's not hard to figure out static analysis or something to warn against those. It's again, it's not a trade-off. But again, just make sure that you will sooner or later, you will see a kernel which does this trick. Okay, clear on this trick? So we're getting towards initializing the CPU. Okay, so, and now let's go back to this example, which I was using here, right? So we got how per CPU variables work. The question is like, why do you need this swap.js instruction? Okay, so first of all, what does this swap.js does? So swap.js uses some other MSR, which points to a location in memory where the kernel can save its own GS base, I think. along those lines. And this base is loaded in the GS. And the current value of the GS is loaded either somewhere in memory, I forget exactly, which is embarrassing, but either to the same value because it's a swap, or maybe to a different location, right? But let's imagine to a different location for a second. So one would say, look, why is this even needed? Because user, if you carefully follow what I was saying, user actually uses FS. Kernel uses GS, right? And why do you even need swap GS? Can you guess? So, and it's kind of like the hint here, this is like safe value, and it looks like this value is untrusted. So why, how can we end up in a case where this GS base value is untrusted? Like Intel is a little crazy. The trick is the following. One would imagine, okay, sure, guys, make sure that this setting GS base is a privileged instruction, like meaning that when you do this write GS base MSR is a privileged instruction which cannot be triggered from ring 3, means user cannot change GS base, and we don't have to do swap GS because we have a GS, right? And user can only change FS, for example, right? Because maybe they can't even change FS because they say, look, write FS base is also a privileged instruction, and the only way for the user to set FS is to do a syscall, and it can be set in a kernel, right? And just to make sure that we understand, why would user change FS to begin with? It's used for TLS. Thread local store. Same idea, thread local, but for user code. Essentially, user code will also have some magical section like tdata, and the runtime, when it starts running, the process will duplicate this. Every time you create a new thread, essentially, not a process, this section will get duplicated, right? And each process will get its own value. Each thread, sorry, will get its own value. So why and what when user needs to change a path? Well, it's useful for compiler people as well, for everyone.
Whenever user
Well, hold on. Why is this trick? I can never maybe explain. Like someone earlier said, it's a hacky way to implement TLS. It was you probably, right? But it's not really a hacky way because it's a very fast way. Because when user code can do something like this, FS full bar, then it's really, really fast. It's like it's the same 1-2 cycles as move instruction or something, right? Because it's adding this FS doesn't introduce a cycle, so it's in the same cycle, right? So it's very clean, because otherwise you can say like, look, I have TLS, which like some kind of a hash table maps to some specific value based on my TAT or something, right? Along those ways. But this is very, very fast. So the goal is to make sure that TLS is very, very fast, so that there are multiple ways to build TLS. You don't really have to. There are architectures which don't have this trick, and then you have to build it in software, right?
I just say it's easy.
Okay, sure.
Yeah, other architectures have like a thread.
Yeah, but I think not all, which is, I mean, yeah, but you can always come up with some embedded board which will not have it, right? And I'm not an expert which ones have and which one don't. So you correct me. But okay, so back to what Talia said. Like, when do we change a fast at user level? So not every time we access TLS, obviously, but when?
whenever it switches to a different thread.
I agree. So whenever it switches to a different thread, right? Or somehow it's and there are multiple ways to build threads. And you say, look, maybe honestly, only when the thread is created, the FS is set once. If it piggybacks on the kernel thread, like in Unix, for example, right? Then you only need to set FS once. But there are funky language runtimes where threads are very, very lightweight. right? Like async, for example, async is a thread in many ways, right? Or like green threads, which like runtime itself, user level runtime switches logical threads on top of one kernel thread, right? And if it's not clear what kernel thread, I can explain later, right? But at this point, every time like you do async something and switch between the threads, you need to update DFS, right? Because you're switching TLS. Make sense? And so Intel, in its own wisdom, I mean, like I'm bitching about Intel, but I don't really know the history, so maybe I'm wrong about it. But they say, look, if you say that write FS is a privileged instruction, then every time you switch a FS, you need to do a syscall. Then the whole benefit of a sync disappears, because if you want to have lightweight user level threads, and each of this does a syscall to change the TLS, then the context switch of those threads goes from like 50 cycles to, I don't know, to like 300 cycles, or only an existing call is probably like, let's say 1,000 cycles at least, but probably even more, right? Just because there is so much overhead in software. And they said, okay, a logical, like kind of like counterintuitive, but logical thing, they said, look, we'll give you a flag. Intel always gives you a flag. They say, okay, the flag will control whether this write FS will be a privilege instructions or not. And if you say it's not, then user can just switch FS very, very fast with this write FS base instruction and ring 3, never do a syscall. Like all the language people are happy, right? Because they suddenly got like a very lightweight TLS, right? Make sense? Make sense or not? Okay, so now this is controllable, whether it's user or just kernel only instruction. And I don't know why, but they didn't give us 2 flags. They said, okay, here's one flag, controls both write GS base and write FS base at the same time. If we had 2 flags, that would be fine, because user can switch FS base, but cannot switch GS base at user level. But there's one flag, it's both or none. And they said, look, if user can change FS, it can also change GS. And if the user is malicious, then on entry to the kernel, like in this example, you don't trust your own GS. And Intel give you instruction to quickly flip GS back to restore it from a saved location, from a saved register. I think it sits in some MSR. It's not in memory. I think it's in some MSR. You get the point? And Talia was asking, what's the difference between GS and FS? Intel, I mean, maybe it has changed in recent years, but Intel's wisdom was that there is only swap GS, but there is no swap FS. Why? I don't know. Like, so that's why you say like GS is always for the kernel. Just because you need to have swap GS on syscall entry to invoke it fast, because there is no swap FS. And you can do it with some additional MSRs, but I mean, probably it's not that much slower, but that's why FS is for the user level, GS is for the kernel, just because there is just one swap GS instruction. Right? And the whole business of it is just because there is no flag which separates GS and FS, right? Okay, we got the point. So now we say, we'll do this swap GS instruction, restore the safe value of GS, right? And after that, GS is trusted, so we save the user RSP into this some whatever global variable. It doesn't have to be this; it could be anywhere, whatever. Load the kernel safe stack GS relative thing. Compiler will generate for us if it's either a CPU like instruction like Japan, or if it's thread local, and then we have a safe environment, right? Make sense? There is a tiny little problem here. When we entered the syscall and about to execute GS, swap GS. So what can go wrong? Just again, an interrupt. Yeah. So what happens if suddenly, when we're about to execute swap GS, interrupt comes, and like it doesn't know that we were executing the syscall. We start using GS tools, even the kernel start using GS, but GS isn't trusted. It's a race, right? So again, bringing it up because Linux solves this race, we have to solve it as well. So how do we solve this race? Correct. That's why we use this in this mask. We say masking R flags, right? Okay, but does it solve all the problems for us? There is like one funky interrupt which does not follow this flag. Which one is this? Non-maskable interrupt. So what do we do for those? Non-maskable interrupt is say, yes, we don't care about this flag, we'll execute it. But you, as a kernel designer, you still have to figure it out how to deal with it. So how? This is. Okay, so how to deal with this in a non-maskable interrupt? NMI comes in, doesn't care about this flag, just goes to the NMI handler, whatever number of words.
So NMI check whether DS has been swapped,
Yeah, so how?
check the MSR.
Yeah, so you're right. So, and remember, I showed this piece of code when we were talking about stack normalization. But really, this is the code. The stack is on 64-bit machine stack is normalized, right? Yes, there is no discrepancy between how many, what is fixed, what is pushed on the stack, whether you transition from ring 3 or from ring 0. So essentially, this is what you can do inside an NMI. You say, look, we'll check for the, like, I don't know where to save the code stack. You have to check whether you are coming from the user code or from the kernel. And if you are in the kernel, let's do swap.js again. And that works because I think swap.js, as I was saying, really doesn't swap the value, but just loads this and loads this in some other location, right? So it's always safe. But maybe I should double check that swap.js really works this way. But it sounds like there is a logic which tells you that it's safe to do. And then you really have swap.js. And there is no race because when you are in an NMI, only one NMI will be delivered unless you until you're on IRET, right? Make sense? Okay, so just wanted to make sure that we understand all these corner cases because it started with just 3 very easy things, but then Intel and everyone let us down, and so it's like everything exploded underneath. So we have to make sure that we handle those arrays. So sysret instruction is kind of opposite to syscall. So it says it will restore from RCX into the RAP, from R11 into R flags. It will restore from, it's a slightly different bits in this. So it's like CS kernel, and next to it, there will be sitting CS user, some bits. So there's a different bits it will restore into the code segment. And the same convention that the user data segment is the next entry in the GPT, and how it matters that the CS and data follow each other in the GPT, right? And after that, this essentially transitions back to here where you invoke the syscall instruction, and you will be in ring 3 again, right? And apparently this mechanism is fast, so because it drops the cost of the interrupt to like really drops the cost of the syscall from 350 400 cycles or even more. I think it used to be that something like within the 100 cycles range. So just one interesting observation is that syscalls themselves at the level of the hardware are reasonably fast. In practice, it probably takes like at least 1 or a couple of thousands of cycles in Linux, because Linux will be doing all sorts of you enter syscall. Okay, so this is what we're gonna build in our kernel with all these things. One other thing which I wanted to make sure we discuss. So how do we pass arguments to this system call from user level? Not a hard question, so don't too hard. What's the easiest way?
However we want.
However we want.
Register.
Yeah, besides that, we can't patch this RCX, R11, or we won't trade this will get overridden. But essentially, yes, we can create our own ABI application binary interface and just say, look, guys, we will like assigns some specific meaning to those registers. I think this is from Linux. So RIX contains this call number, RDI, and it follows kind of like system by convention because RDI is the first argument on sides 2 up to some number. You can, in our homework, we can fix any, and you say like, what if I need more? At some point you have to stop, and then this can be a pointer to additional argument. So whatever you want to do, it's kind of not our fault, like this. So that's what we want to implement, and the return is kind of symmetrical. So from this syscall dispatch, we'll restore registers, prepare to return, loading the user RIP into this RCS, user of into 11, user speakers into RCP. So this point is stack. Again, we're racing the level, so you have to these interrupts and so GL. This ref Q is a instruction, right, which returns you to the user level. Right? Makes sense? So any questions? The only thing which I have left is like take a couple of code examples. So because this is just like some bizarre example. One of you might ask a question, why is it I'm switching between these two kernels, Redleaf and Atmosphere? So Redleaf did not use hardware rings for protection. It was only using safety of the Rust language. So it runs, everything runs, userland in the kernel runs in ring 0 because it's kind of like we trust the compiler to create an abstraction of a process correctly for us. It's not easy in Rust, but it's doable supposedly with our tricks. That's why it doesn't have syscall. So I cannot show a syscall in Redleaf. It does have this thread local, and this is where we build it. And Jafang in Atmosphere built CPU, but in Redleaf, if you search for thread local, you'll find a bunch of instances, but there is no syscall. That's why I have to jump back to Atmosphere to essentially show you the syscalls. And the syscalls in Atmosphere, again, it's debatable how, like, the cleanness. Oh, sorry, is that what we're doing? Debatable the quality of the code, but at a high level, what we're doing here, like this is the code which prepares those registers, like as I was saying. So with this S star registers with those, like this is the instruction pointer. We're just writing an MSR. Those bits of this L star register, which is what is it we're doing? Sys entry, and what do you do to S star? So this is the, I forgot exactly, but okay, you can figure it out. This is another register to even, you need to set it just to even enable the syscall extension, because by default it's disabled. So on Intel you have to say, look, if I want to use syscall instruction, I have to write this MSR as well. And then Xiaofeng here has a bunch of like array of system calls where he like says, okay, I'll have different system calls implementations. And then he relies on that's his API, which is probably either similar or identical to Linux. But essentially he uses a naked function similar to how we were doing for sys, like for interrupt entry and exit. Hello, your community knows something about naked functions. But essentially what he does here, this is his stack offset, which he passes here to the macro somewhere at the bottom. Let me show you. Somewhere here, probably, right? I forgot how to stitch together, but along those lines. But what he does essentially, he does a similar thing. So he starts with, where is his swap.js actually? So he probably assumes that user cannot modify JS base, and essentially he skips swap.js altogether. Just in this kernel, he says, okay, we're not going to support TLS for user level, so he just skips it. Then he just saves everything in a format probably similar to whatever the layout of the data structure he wants to get. He actually, instead of calling a generic syscall dispatch function, which I would recommend you, he saves a couple of cycles here by just dispatching directly from this array, right? So he compares if the syscall number, which is passed inside array_x, is in range of this array, and then just jumps to calls the syscall here from the array. That's probably not worth it. Then he has a specific cleanup of logic, but at a high level, idea is use this naked assembly similar to how we did it for interrupt entry and exit, create your own data structures, and you will be just good. So probably the very first syscall which you're going to build will be something like print, so you can essentially say hello world. Makes sense? Yeah, so not super hard. When I will be working on the homework, I will add those links, so you will be able to follow and figure out, like, at least like just of the code. One other minor point I forgot to say. Since Rust by default generates it thinks that it generates user level code, then this thread local macro by default will be using fs as a base, right? So you need to tell the Rust compiler that please use GS instead of fs to generate the code. So because for the kernel code, right? So that then the compiler will start using GS really fast. Okay, so I think this is all. This is what I wanted to say. All good. Yes, this goes okay. It took us the whole lecture, but yeah. So the point is that you will see the similar code, even like it's a little bit of an overkill to do it for the kernel, which is as small as ours, but this is kind of like the state of the art. And so when you start working, so next time you see something like a fast in when you debug GDB your user level code, it means that it's thread local variable. The GS in the kernel means it's a per CPU variable in Linux, stuff like that. So that's also